Yeah.
I already have. Not many people watch them, I mean, with the followers.
Yeah, I mean, art, but it's not a lot.
Yeah, yeah.
What I mean, once you do one, all of them.
Yeah,
Because what I show them, like, all of them follow that form
Yeah,
with different things.
yeah,
Once they recognize that they all follow this, almost all of them,
yeah.
I think you get fun. So are we gonna get staggered?
Yeah, me too. That's the base story today.
All right.
And Polymer.
So this, I just think everything that
Talk about this food.
you have anything funny being going the in with the
We did hydrogen bonding on Tuesday.
maybe not I did I can't remember.
We did this, and then even before that, we did some examples there as well. Yeah. So we're done with hydrogen bonding. This was straightforward, right?
Yeah.
And this is the one. Yeah.
It'll play a role with it. Like what makes it better with us.
Right.
Like
All right. Good afternoon, everybody. Happy Thursday already. All right. So tomorrow we're gonna have a quiz. I cannot remember which number it is. I believe it is 6. So we will have maybe one more quiz for the semester, I think. We're done with all the quizzes, and maybe we're already done with type A exams, online exams, but quizzes are maybe one more left after this, I think. Okay. So let's see. We are not going to be meeting next Tuesday. Okay, it's good and bad news at the same time. Meaning on Thursday we might have to cover a little bit content before we get into reviewing. However, my dream for today is to get into polymers. Okay, to get you guys started on the polymers, and I've already posted like everything that you need to know about polymers on D2L. I'll post another video. Like an intellectual video on polymers as well. And we will definitely complete the mixing today, which is going to be the last topic in Unit 3, Module 1. And also in Unit 3, Module 2, like I said, I will begin the hard part of Unit 3, Module 2, which is like the first part, which is going to be new to you. After that, it's going to be pretty straightforward. Okay, so that's going to be the dream. I just need your cooperation today. I want you to pay attention and then make sure that you learn the stuff. That's all I'm asking you to do. Help me help you learn. Yeah. Okay. So with that, let's start with discussion before we get into mixing. I'll give you a minute. Go ahead. Yeah.
I take that same.
it's probably I just like this picture.
Yeah, right. All right. So I will not close the question yet, but just to remind you about the objective here. So if you can remember, we compared the different intermolecular forces, okay? And we noticed how dispersion can be the weakest one if you compare the weakest of dispersion forces, the weakest of dipole-dipole and hydrogen bonding. However, the strongest of the dispersion forces is same as the strongest of dipole-dipole and hydrogen bonding. Meaning, this is the take-home message here, the dispersion forces can be as strong as dipole-dipole or hydrogen bonding interaction. In some occasions, actually, they can be even stronger than hydrogen bonding and dipole-dipole interactions. Okay. So the objective of the activity I have just opened for you is that to recognize that dispersion forces can be strong as strong as or stronger than the dipole-dipole interactions, provided that you have enough electrons. Okay. So going back to our problem at hand, okay, these are the details given to us. We are given the boiling temperatures of all the substances. Based on that, we see that oxygen has the lowest boiling point, meaning weakest intermolecular forces, and CCl4, on the other hand, being a nonpolar molecule, has the highest boiling point, meaning the strongest intermolecular forces. So if you do a bar chart for this, I actually started doing this over here. Let me zoom out. Okay. So if you do the bar chart, so oxygen, is it polar or non-polar, by the way? Yeah, it's non-polar molecule. Therefore, it only has dispersion forces. CHF3 is polar or non-polar? Yeah, it's a polar molecule. Therefore, on top of dispersion, it has dipole-dipole. And also, because it has 34 electrons, its dispersion forces must be twice as stronger as that of oxygen as well, because of the greater polarizability. Here are the dispersion forces of CHF3. And on top of that, it has dipole-dipole forces as well. Okay. So that explains why we have 190 Kelvin boiling temperature of CHF3 compared to 90 K boiling temperature of oxygen. Br2, on the other hand, has a boiling temperature of 332. Okay. So meaning it should have a very high bar. I'm running out of space now. That's okay. All right. And Br2, is it polar or non-polar? Yeah, it's a non-polar molecule. There are no electronegativity difference there. So it should be just dispersion. And CHCl3 is a polar molecule, just like CHF3, but it's going to be less polar than CHF3. And also dispersion forces must be stronger than CHF3. Let's see if we can indicate that. I would say dispersion forces wise go up to this point. Okay. And then the rest of the contribution must be from dipole-dipole. Okay. So 332 Kelvin boiling temperature in Br2 versus 334 Kelvin boiling temperature of CHCl3 is justified using the dipole-dipole contribution. And then CCl4 has the highest boiling temperature, meaning it should have the strongest of intermolecular forces. So CCl4, is it polar or non-polar, by the way? Everybody, CCl4 is polar or non-polar? It's non-polar. Remember, if we have a perfectly tetrahedral molecule with like the same 4 atoms bonded to carbon, it's a non-polar molecule. But as soon as you replace at least one of them with something else, it's going to become a polar molecule, just like CHCl3 and CHF3. All right. So this is going to be my, this is going to have only dispersion forces. Okay. So now we see that even though some of these are non-polar molecules, they have stronger overall intermolecular forces compared to polar molecules like CHF3 versus Br2, right? Now, if you compare the number of electrons, so compared to CHF3, how many more electrons does Br2 have? Can we count? Like we have 70 electrons in Br2 and 34 electrons in CHF3. How many more electrons does the Br2 have? It has 36 more electrons. Thank you. Okay. So meaning if you have 36 electrons, that is enough to outweigh the dipole-dipole contribution of the polar molecule for the non-polar molecule. That's one. But let's not stop there yet. Okay? We have another situation like that. CHCl3 is polar, CCl4 is non-polar. And let's see how many more electrons does CCl4 have compared to CHCl3. How many? So CHCl3 has 58 electrons, CCl4 has 74. How many more electrons does CCl4 have compared to CHCl3? 16. Yeah, 74 minus 58 is 16. So meaning if you have 16 electrons, that is enough for the nonpolar molecule to outweigh the dipole-dipole contribution. So this leads us to a fake rule called 15 electron rule. Okay. I call this a fake rule. The reason is we only use as a last resort if somebody, you know, is forcing us to predict, let's see, predict the overall intermolecular forces comparing polar versus non-polar molecules. Okay, so that's the only time we're going to be using this, and it goes like this. If the relatively non-polar molecule contains 15 or more electrons than the polar molecule, the dispersion forces may outweigh the dipole contribution. Okay. You don't. I will never ask you to write or define the 15 electron rule or anything like that, because you know that I do not ask boring questions like that, right? Okay. So I just want you to, you know, use this as a guide when we are deciding whether the non-polar molecules can have overall stronger intermolecular forces than, you know, than polar molecules. Okay. If we have to predict, it's the only time we'll be using that. Okay. All right. What questions, concerns, comments? Laila, can I have the microphone with Laila, please? Okay. Behind you. Closest exist can be behind you. Anyway, sorry. Laila, go ahead.
Why is it relatively non-polar molecule, not just non-polar molecule?
So, how do I answer this? Okay. No, that's a good question. Okay. Now, if you can remember, HCl versus HBr. This is HBr. We did this the other day, but I mean it's somewhere else, and we compare this to HF as well, which has the strongest. Okay. So now both HCl and HBr were polar molecule. Yeah. However, HCl was more polar. Therefore, let's say that something like this. So if this is dispersion forces, this is going to be the dipole-dipole, and HBr is primarily dependent on the dispersion forces, and there was some dipole-dipole contribution, but it's weaker. Now, if you compare these two, HBr is a relatively non-polar molecule relatively to HCl. Do you agree, Laila?
Yeah.
Okay. However, this had 36 electrons, and this had 17 plus 1, 18. I think 18. 18 electrons. Okay. But overall, HBr had overall strong intermolecular forces. Why? It had more than 15 electrons. We didn't talk about this the other day. I didn't want to get into that. And nobody asked as well, which is good. Okay. But this was the reason.
Okay.
Yeah. So they're relatively non.
Okay.
All right. Okay. Any other questions, concerns, comments at this point? Okay. All right. If that is the case, we are done with that part. Now what I want to do is I want to get into mixing. Okay, we started talking about mixing the other day. Let me remind us about what we have done so far. We talked about the intermolecular forces between these two molecules. Okay. So now what we want to do is we want to predict whether given two things would mix or not. Okay. So prediction and explanation, that's all we do when it comes to mixing. Now, here's what I'm going to do. I'm going to give you a mantra. Okay. We can use that mantra to predict whether two things mix or not. And it's really easy and easy to remember as well. You already know this. Okay. It goes like this. Are you ready? You should write this down. Okay. Like interacts with like. Yeah. Like interacts with like. Can we write that down together? I'll do it too. Okay. That's the mantra. Okay. You can call it a mantra. In fact, I encourage you to call it a mantra. Okay. So the mantra is like interacts with like. Okay. Now, what do I mean by this? Okay, mantra. It sounds like alchemy now, you know. The chemistry was used to be called alchemy, you know, a long time ago. And they used like plant stuff and extracts and stuff like that to make potions. I don't know, it sounds so cool, like a gothic game. All right, anyway, so that's the mantra. Now, what do I mean by this? Okay, so let's say that somebody, you know, I mean, after getting their paycheck on Friday, goes to a place called those bars. And, you know, there are places called bars, okay? Clubs or whatever. Anyway, so, and they take this molecule and they want to drink this, okay? They cannot drink this alone because it's going to be really toxic if they drink this by themselves. What they're going to do is they're going to ask the bartender to mix this with this. Question, would they mix with each other? By the way, does anybody know what we call this molecule? What is this molecule? Somebody should know. I know somebody knows it. Nobody knows it? Yeah, that is ethanol. Ethanol is the technically correct term, but people call it alcohol in general. So CH3, CH2OH. Okay, our line structure is this. This is called ethyl alcohol or ethanol. By the way, people call it alcohol, but I mean, this is not the only alcohol. I mean, if we have like this, CH3OH, that is called methyl alcohol or methanol. If you have like CH3, CH2, CH2OH, that is called propanol or propyl alcohol. So there are many alcohols. They're coming from, by the way, when the Arab was, you know, those Arabian countries were like, you know, used to be at the top of science. Okay, that's why the alcohol, that name comes into play. Anyway, it's a different story. And by the way, so these are different types of alcohol, and this particular one is called ethyl alcohol, but people just call it alcohol for some reason. Anyway, the question is, would they mix with each other or not? Now, how do we do this? We think about the interactions they can have. Let's think about the ethanol molecule, this molecule over here. Is it polar or non-polar, by the way, to begin with? Everybody, it's a polar molecule. Thank you. So what types of intermolecular forces can it have with itself? Can it have dispersion forces? Yes. Can it have dipole forces? Yes, DD. Can it have hydrogen bonding forces? Yes, it has hydrogen covalent bonded to oxygen, right? Therefore, it can have hydrogen bonding as well. Now let's look at water, H2O. Can it have dispersion? Yes. Can it have dipole-dipole? It's a polar molecule. Polar molecules have dipole-dipole. Can it have hydrogen bonding? Yes, it can have hydrogen bonding as well. So these two molecules have like interactions, right? So if they go to a party, they will talk to each other. Okay, because they have, like interests, so they have things to talk about. Okay, so if they go to a party, they will talk to each other, therefore they will mingle or they will mix or they will be soluble. So whatever you want to call it, okay? Don't call it mingle though. Mingle doesn't fly, okay, with our TAs. So let's call them, they're going to mix. That's the prediction. Why? They have like interaction. That is what is meant by like interacts with like. Okay, because they have like interactions. All right, now let's take another example. Okay, so if you have a gasoline car, I don't know, like vehicle, right? So that has a compound called octane. Octane has 8 carbons. Let's try to draw it, okay? We have 1, 2, 3, 4, 5, 6, 7, 8. Here's octane. And now let's think about whether octane can mix with water or not. Here's octane. Here's water. Okay. Now let's think about this. Octane. Is it polar or non-polar? Everybody, please. Thank you. It's a non-polar molecule. Why? It is a hydrocarbon molecule. It has only hydrogen and carbon. Therefore, it's going to be non-polar for all intents and purposes. If that is the case, what type of intermolecular forces do we expect there between those molecules? What is that again? Dispersion forces. What else? What else? Dispersion forces and what else? Everybody. That is it. Okay. Non-polar molecules can only have dispersion forces. Okay. So on the other hand, water can have dispersion, dipole, and hydrogen bonding. Okay. Guess what? If these two go to a party, rather than they two talking to each other, they will talk within themselves. The water will talk with other water molecules, because why? They have more like interactions. Okay. And the octane molecules will talk to themselves. They'll talk to other octane molecules rather than talking to water. Why? They don't have like interest just like water. Okay. So therefore, what do you think? Will they mix or not? No, they won't mix. Okay. They are not going to mix. So let's write not mix. That's the idea about predicting solubility or mixing of covalent compounds. Like interacts with like. All right. With that, I'll open the puppet question. Here we go.
Let's see if I can. Just gonna be like
All right, we have close to getting closer to 90% responses. Okay, I'm going to close this question in 5, 4, 3, 2, and 1. And here are our responses. Okay. Okay, these are the most popular answers, and these are the correct answers as well. Almost 90% of us said the same thing. Okay. So this is sugar, by the way. C12 is 22O11 is sugar. This is the same molecule. It's a polar molecule, and obviously it has like interactions with water. Therefore, it's going to be soluble. This molecule is a non-polar molecule, insoluble in water. O2 is non-polar. Again, I don't know why it is 159. O2 is a non-polar molecule because, the electronegativity difference. People tend to forget this. We tend to forget this. Please don't, okay? So it is not just the electronegativity that determines whether a molecule is polar or not. This is the electronegativity difference that we are looking for. We have 2 oxygen atoms. So therefore, there's no difference in negativity values. That's why O2 is a non-polar molecule, okay? It's true, it's a highly electronegative atom, but there's no difference in electronegativity to make it a polar molecule. Anyway, it's non-polar, therefore you can predict it to be insoluble in water. And ethyl alcohol, as we discussed, it has similar interactions like water, therefore they will mix with water. That's why it is soluble in water. Okay. Any questions, concerns, comments at this point about predicting solubility of covalent compounds? Okay. All right, we're done with predicting. Now it's time to bring out the big guns, the Peg diagrams. Yeah? Oh, yeah, they are back. They are back. Okay. All right. Now, just to remind us, Peg diagrams are used to explain things. Okay, that's the main idea of Peg diagrams. Okay. Now, here's how it goes. Just like any other process, okay, mixing is the process as well. If mixing is the process, they have 2 states. The initial state, which is the unmixed state, and the mixed state, which is final state, which is the mixed state. Okay. So if you think about having substance A mixing with substance B, in the unmixed state, we have A interactions and then B interactions. A interacting with other A's and B interacting with other B's. And in the mixed state, we have A interacting with B. Okay. Now, I want to tackle a little bit more, one more question than what you see on the screen. Okay. Just to remind you, I think the first one is easy. What is on the screen is easy. So they are telling us AB intermolecular forces are stronger than the AA and the BB intermolecular forces. In other words, the intermolecular forces or interactions in the mixed state are stronger. That's where we have the AB interactions. Then the interactions in the unmixed state, where we have the AA and the BB interactions. If that is the case, what can you tell me about the potential energy of the mixed state compared to the unmixed state? Should it be higher or lower? Lower. Okay, remember, the stronger the attractive interactions, the lower the potential energy. If AB are stronger, or if we have stronger attractive interactions in the mixed state, then you should have a lower potential energy in the mixed state. That's what they're asking there. Okay, so we're done with that. Now there's another part I wanna add, which is not relevant to this and maybe not relevant to the next one as well. Kind of relevant, but they're not testing that at least. Okay, so if two things are mixing, look at those diagrams now. Okay, so the unmixed state, the red particles and the blue particles, and the mixed state, the blue mixed with the red particles. It's like having a party in the mixed state, right? Anyway, so my question is, where do we have a higher number of configurations if two things mix? In the unmixed state or the mixed state? Can you write the answer on your whiteboard? Right, M or UM? Where do we have a higher number of configurations? M or UM? All right. All right. All right. Can I see your whiteboards, please, everybody? Can I see the whiteboards? Yeah. We see, look around. We see mainly what set do you see? We see M, the mixed state. Yeah. So if two things, so that's okay. If two things mix, then the mixed state tend to have a higher number of configurations. Okay. So I mean, you can think of that in many different ways, but that is the case. So therefore, you will hear about this or read about this. Okay. Solubility or mixing is kind of driven by number of configurations. The reason is, if two things mix, the mixed state is going to have a higher number of configurations. Okay. And then this is how we are going to be defining general solubility. I mean, if something is generally soluble or generally mixing, what that means is the mixed state has a higher number of configurations. Now, here's what I'm going to do. I've already posted something on your D2L. How many of you were able to watch the video I posted about mixing on D2L? Can I see the hands? Anybody? I saw at least one hand. That made me happy. At least one person. Thank you. Okay. Now, anyway, let me show you what I mean. Oh my goodness. Can you do this? Thought that I now wrong. Bear with me for a second. I need to point this out because all right. Give me 1 second. Okay. So for the moment, I only posted 2 videos. Okay. I have a bunch of other videos I'm going to be posting just to help you complete your notes. Okay. And also I will post an entire lecture video on unit 3 module 2, the polymers, so that you will be ready, by the end of this weekend for unit 3 exam or exam 3B. Okay. Anyway, so mixing of covalent compounds. I don't want to hear myself. This is good. Okay. So here I'm going, what's going on here? I'm going over the entire mixing process, mixing concept. Okay. Like interacts with like, predicting solubility and everything like that. Oh, I use the same example, but heptane. Anyway, so, and there are 6 possibilities when it comes to the peg diagrams of mixing. I'm going over each and every, each one of those peg diagrams relevant to mixing. Here, let me show you what I mean. Okay. So here's one of them. Okay. So if you have this peg diagram, we see that the mixed state has a higher number of configurations. Therefore, this tells us that these 2 substances we are talking about are generally soluble. Okay. This is generally soluble situation. And because the mixed state has a lower potential energy, it is favored at what temperatures? Low temperatures or high temperatures? Those are 2 options, low or high. Okay. All right. Yeah. So this is a reminder. Okay. So the reminder is we talked about this in Unit 1, Module 2. High temperatures favor the state with high potential energy. And we talked about why as well. Okay. The reason is at high temperatures, particles are moving faster. When they move faster, they cannot have strong interactions. And then we talked about this using the song called, you remember the song? Despacito? Yeah, yeah. So if you want to have strong interactions, you need to slow down. Okay, just like the song says. Anyway, that's the idea there. So high temperatures favor the state with high potential energy, meaning low temperatures would favor the state with low potential energy. Therefore, in a situation like this, increase in temperature, that's what I'm writing now, increase in temperature will decrease the solubility. Why? It's going to start favoring the unmixed state a little bit. Only a little bit. The reason is the mixed state is in the nice corner here, but we'll talk about the nice corners when we talk about ionic compounds. But anyway, now this is one. And here's another situation where mixed state is in the other corner. When that is the case, this is generally insoluble. Why? The mixed state has a lower number of configurations. And because the mixed state has a higher potential energy, increasing temperature will increase the solubility. Okay, let's look at another one where the mixed state is at this corner. So again, the mixed state has a higher number of configurations. Therefore, this is going to be generally soluble because number of configurations tells us whether it is soluble or not. Okay. And then because the mixed state has a higher potential energy, increasing temperature will, what do you guys say? Increasing temperature will increase the solubility or decrease the solubility? Everybody. Increase the solubility because mixed state has a higher potential energy. Increasing temperature will start favoring the state with higher potential energy. So that's why I'm writing high temperatures, increasing temperature will increase the solubility. Okay. And then here's another one, the fourth one, mixed state at this corner with a lower potential energy, lower number of configurations. This is going to be generally insoluble. Okay. Generally insoluble. And I write that here, generally insoluble. I started writing general stuff like here, but they are relevant to the first two diagrams as well. Anyway, because the mixed state has a lower potential energy, increasing temperature will decrease the solubility. Oh, I posted the video here. You don't take pictures. I posted the video on Doodle already. Okay, so you can use that. Now, two more to go, and that is going to be looking like this. So sometimes the unmixed and the mixed have the same potential energy, meaning their intermolecular force strengths are like comparable. Okay, if that is the case, potential energy will be similar in the unmixed and the mixed state. However, if the mixed state has, oops, what here? I don't. Okay, mixed. All right. Anyway, that's all I can do. Anyway, because the mixed state has a higher number of configurations, it's going to be generally soluble. Now, how does the temperature affect here? Because the potential energy is the same, increasing or decreasing temperature will not affect the solubility. Because the potential energy of the two states are the same, increasing or decreasing temperature will not favor one state over the other. And the last possibility of the six-peg diagram is this. Because the mixed state is at a lower number of configurations, is generally insoluble. And then again, increasing or decreasing temperature will not affect the solubility. Why? None of them is favored by potential energy. That's it. So everything is summarized over here, and then this is available to you together with introduction to polymers in our D12 side. All right. Any questions, concerns, comments so far? Okay. So with that, let's play with some peg diagrams. For the time being. Here we go. Start with this. So, All right. I'll give you 30 more seconds. Please submit your answers. Today, I'm going to wait until I get 80% responses before I move on, not 90%. All right. I'm going to close this question in 5, 4, 3, 2, and 1. And here are our responses. Most of us selected option A. That's the option I would have selected as well. Okay. The reason is you are told that AB interactions are stronger, meaning mixed has stronger attractive interactions, meaning mixed should have a lower potential energy. That's the idea there. Okay. And then I would give credit for 4 as well, option 4 as well here. The reason is you are not told that they are generally mixing or generally not mixing. For that reason, if you even select 4, I would be okay with that based on strength of intermolecular forces. Okay. But my go-to answer here would be option 1, like most of you selected. All right. Any questions, concerns, comments at this point? Okay. Let's do another one, just for fun. By the way, that video there covers all 6 possible pig diagrams, okay? Any question about the pig diagrams, about mixing, we should be able to tackle with that video. I mean, just make a small note after watching that video. So I think it's a 15-minute video.
Monday, yeah.
All right. So we have there should be enough time for this question. I'm going to close it in 5, 4, 3, 2, and 1. And here are responses. Okay, so these are options. Some of these are correct. Okay, and most of us selected C and D. So let's see, at least, I mean, I haven't thought about it. Yeah. So those are the correct answers. Why? One more time. So if the solubility is increased by increasing temperature, that means the mixed state has a higher potential energy. And there are only 2 Venn diagrams with mixed state at a higher potential energy, and that is option C. Here's the mixed state with at a higher potential energy, and D. Okay, with the mixed state at a higher potential energy. That's why C and D are the answers. Okay, if you want to increase the solubility by increasing temperature, the mixed state must be at a higher potential energy. That's the idea. Because high temperatures favor the state with high potential energy. Right? I'm going to clear my doodling, reopen that. Don't change your answer if you don't understand it. You need to ask questions. But let's do one more, and then I want to move on to polymers. Last question from here. I will bring this up again on Thursday. We are not meeting on Tuesday. I will bring some of the big diagrams on Thursday as well, just as a review. Okay. Oh, and you will see big diagrams on your quiz tomorrow. All right. So I'm going to close this question in 5, 4, 3, 2, and 1. Hey. All right. So most of us selected option C, and that is the correct answer as well. Now let's think about it. We are in peg diagram A. In A, the mixture has a higher number of configurations, meaning it's generally soluble, because number of configurations tells us that. And then the mixture has a lower potential energy, meaning decrease in temperature will increase the solubility, or increasing temperature will decrease the solubility. So one of those, depending on how they're phrased. So it's generally soluble in acetone, but increasing temperature will decrease the solubility. Why? Okay, increasing temperature will favor the state with higher potential energy, which is the unmixed state. That's why the increase in temperature will decrease the solubility. Okay, this decrease will be very slightly though, because the reason is the potential energy and the number of configurations both favor the mixed state. In this case, they are soluble at all temperatures, but increase in temperature will decrease the solubility slightly. Okay. Anyway, that's a story for a different day. Okay. What questions, concerns, comments do we have at this moment? Anything? Now, if you haven't made a note about this, okay, at least writing one sentence about the general solubility. Okay, if something is, if two things are generally soluble, the mixed state has a higher number of configurations. If you can write that down, that will help you a lot. Okay, if two things, one more time, I'm going to repeat that. If two things are generally soluble or generally mixing, then the mixed state will have a higher number of configurations. Okay, that will solve half of your problems when it comes to the peg diagrams of mixing, covalent compound mixing. All right. So with that, I mean, I have a few other questions about peg diagrams, but I want to move on to a preview of coming attractions. Okay. All right. So we are in Unit 3, Module 2 now. We are starting Unit 3, Module 2. Now, it's really simple what we do here. Really simple. Okay. Only thing we do here is we apply what we learned about intermolecular forces to larger molecules. Larger means macromolecules or polymers. So these polymers can be natural, like DNA molecules, so polypeptide or protein molecules, or they can be synthetic, like polyethylene, Teflon, PVC. Okay, maybe you are dealing with some of these in the lab these days, right? Are you dealing with the plastic lab? Yeah, so you're dealing with the polymers these days. Okay, it's the same thing, same idea here. All right, now here's what we're going to be doing. First, we'll understand the polymers. Actually, that's all we're going to do today. And then when we come back on Thursday, we will talk about applying intermolecular forces to polymers. It will take about 10 to 15 minutes, which is much easier. Okay. Now, here's what I'm going to be doing. So polymers, when it comes to polymers, you need to do two things. Actually, not more than two things, but you need to know two things about polymers. There's something called the polymer, and then the polymer is made of something called monomer. You need to know both of those things. Okay? And if you are given a monomer, you should be able to tell me the polymer from that. If you're given the polymer, you should be able to tell me the monomer from that. And you will have at least 2 questions on your exam 3B about that. Being able to tell me the polymer from the monomer and monomer from the polymer. I'm telling you the questions. Okay. Anyway, so let's think about this. What you're seeing on the screen is called polyethylene. Does anybody have polyethylene right now? Or maybe at your apartment or home? Anybody? Can I see the hands? Polyethylene? Nobody has polyethylene? Anybody who has interacted with polyethylene? Okay, at least a few people. So, seriously, do you go to places like Safeway, Price, Albertson?
Oh, I do, but I don't like it.
You don't look at the polyethylene? But here's the thing though. Whenever you buy groceries, they give you a plastic bag, right? Guess what? That plastic bag is made of polyethylene. Don't you have those? You should. Okay, that is polyethylene. All right. Anyway, so I'll give you another example. All right. Now listen to this. So this is the polyethylene structural formula. This is the polyethylene polymer structure. It's huge. We cannot draw the entire thing. So what we do is when we write the polymer in our notes, we use a structural formula which looks like this. And this is the monomer which the polyethylene is made of. I'll come back to this. Okay. Now what I'm going to do is I'm going to replace one of the hydrogens in this monomer with just one atom, chlorine. Okay. When I do that, I get this polymer. Ignore the third line. Okay. Pay attention to the second one over here. Second row. Only thing I did there was I just replaced a hydrogen with a chlorine. You get a new polymer called polyvinyl chlorine or chloride. Is it chloride? Yeah, polyvinyl chloride. Okay. Now, does anybody have polyvinyl chloride at home? Where? You have it? Okay. Okay. All right. Does anybody know what polyvinyl chloride is or PVC? Does anybody have PVC at home? Thank you. They're used to make pipes. In contrast to using polyethylene to make plastic bags. Okay. So what is stronger, PVC or polyethylene? PVC is stronger. But guess what? There's only one difference. I just replaced one of the hydrogens with chlorine. Now, here's the question. Why? Why is PVC much more stronger compared to polyethylene? Why? What makes it stronger? Anybody? You already know the answer to this. Yes, sir. Remember name, sir? Andrew, why? Thank you. The intermolecular forces are stronger, right? And then, like Andrew mentioned, we have dipole forces in polyvinyl chloride, which we do not have in polyethylene. On top of that, actually, you know what? That is on top of stronger dispersion forces. Remember, I replaced a hydrogen which had only one electron with chlorine, which had 17 electrons. Now, we have much more electrons in our polymer, making the polymer more polarizable, meaning polymer is going to have stronger dispersion forces on top of dipole forces. Then that's why we use PVC to make pipes and polyethylene to make bags. Okay. And the last polymer here is called Teflon. All right, this is a horrible polymer. Does anybody have Teflon at home? Yeah, I mean, if you have like non-stick pans or something like that, they used to coat that with Teflon. Why? Teflon doesn't react with anything. It doesn't interact with anything. Even water rolls off the surface of Teflon. Okay. Anyway, it's a huge problem because they have found that you see Teflon in the blood of newborn babies. This is a huge problem. Okay. So anyway, we are trying to get away from Teflon and then going with some other stuff. But anyway, that's for you. All right. Now let's think about drawing polymers and polymers from monomers and monomers from polymers. I mean, I need to get that straight at some point. Like which one I want to do first, but I'm going to do it this way. So it's really easy if you understand what's going on. So you have to pay attention though. That's the only requirement. If you have your phone, if you're on your phone, that's not going to be helpful. Okay. Sorry. That's okay. That's okay. All right. That's going to be helpful. Please pay attention now. If you get this once, it's going to be much easier for you. If anything you get from the polymer. Here's how it goes. So polymer is a huge molecule. So let me draw the polymer. Okay. So let's say that we have a polymer like this. Okay. And then we have something sticking up like this. Okay. By the way, this is line structure. I mean, you can do the same thing with Lewis structures as well, but I'll stick with the line structure because I'm lazy. I mean, it is easy, right? Okay. Now, you should see a pattern here. Okay. So the pattern is 2 carbon atoms are repeated over and over and over. So you can pick any two carbon atoms from here, any two. I'm not even kidding. Okay. You can randomly pick any two carbon atoms from this chain, and then you're good. Okay. So let me pick any two. I'm going to pick that. I'm going to call this 1 and this is 2. Randomly. Okay. You see that this is repeated over and over. Here's 1 and 2. Here's 1 and 2 one more time. Here's 1 and 2. 1 and 2. So it's like recognizing patterns in, I don't know, music or something like that. Right? So that is repeated over and over. Now here's what I'm going to be doing. If I just take that part within parentheses and redraw, okay, so I'm going to draw 1 and 2. Here's my 1. Here's my 2. Here's X sticking out from 2. Okay. And if I drew parentheses around it and write n here, which n can be like 10 to millions, very large number, okay? And I got myself the polymer structural formula. I drew like two bonds coming out from 1 and 2, just to show that they are connected to each other. Okay? This is known as the structural formula of the polymer. So I'm going to rewrite this. This is my polymer. Okay. This is specifically known as the structural formula. Sometimes they just refer that to as polymer, just polymer. Okay. Now we are not done yet. So we just have the polymer now. Okay. What about the monomer? How do I get the monomer? Again, I go to the repeat unit. What is repeated? These two carbon atoms, right? I just draw that. Here's the two carbon atoms repeated. 1 and 2. I write them down. 1 and 2. And to 2, I have X bonded. So I write that too. Now here's what I'm going to be doing. Instead of drawing two bonds coming out and through these parentheses, I am going to introduce a double bond between 1 and 2. Yeah, that's my monomer. That's easy. That's all you have to do there. Okay, that's my monomer. I'll do another one, but maybe let's go the other way around now. Okay, so I got a monomer from the polymer. Now let's go from monomer to polymer. I'll do something randomly. I don't know. Okay, so here's our monomer will always have a double bond. Okay, let's say that I have something like this, an antenna like that. That's my monomer. You are given the monomer, and then they're asking you to show the polymer from this. Okay, so what do? I draw the, I'm going to be drawing the monomer one more time without the double bond. So let me call it 1 and 2. Here's my 1, here's my 2. Let me draw 1 and 2. Okay. Here's my 1, here's my 2. Okay. I know that to my 1, I have an antenna attached. It's not an antenna, it's just another like something which I don't care. Okay, something like this attached. Okay. Now, instead of drawing a double bond between 1 and 2, I'm going to draw parentheses around it. I'm going to draw parentheses and write subscript n over here. Okay, and then I'm gonna draw two bonds coming out from 1 and 2, and that is my polymer. Done. So I went from monomer to polymer now. Initially, I went from polymer to monomer. Now I went from monomer to polymer. That's all you have to do. It's really simple. Yeah. Okay. All right. Yes. I talked to Alexis first. Can I talk to Alexis first? I'm come back to you. Okay. Alexis, go ahead. What did I do? Did I do something wrong?
No, I'm just getting clarification. So the double bond is just an indicator for the bond that would be present in the structural formula.
Learning assistants, can I have you here for a minute? Oh, Alexis, I'm going to show you the reason why we have a double bond in. I want all the learning assistants here for a minute. You know what I'm talking about. Okay. All right. Now, can we try to show them the importance of double bond? Okay. So let's assume my learning assistants, okay, are my monomers. So when they're monomers, you have a double bond. Can you do this? Okay, now they are my monomers. Okay, when they become the polymer, they are going to break the double bond and join hands. Can we do that? Now it's a huge molecule. See, that's my polymer. One more time. Can we do the monomer? Monomer with the double bond. Okay, so when they become the polymer, they break the double bond, join hands. Now we have huge polymer. Okay, thank you so much. So, Alexis, that's why we have a double bond.
Okay, thank
Yeah?
you.
Laila. Laila, go ahead.
So I noticed on the graph that the polyethylene had the like circular sort of brackets, but the
Oh, it doesn't matter.
polyvinyl
Yeah,
it doesn't
so
matter.
the shape of the bracket doesn't matter. It can be square, it can be circular, it can be squiggly. It doesn't matter.
Okay.
As long as we have parentheses and a subscript n to show that they are repeated over and over. Yeah?
Yeah.
We have a question all the way there, Peyton, if you can run. Thank you so much. You have to remind me your name, miss.
Elise.
Elise, go ahead.
So my question was in the first example, it said n equals 10 minus 10 to the 6.
Yeah.
And in the second n, like example, it just had n. Is that fine just to have
Oh,
n,
yeah.
or do we have to?
So no, I mean you don't write so you do not write this all the time, okay? I just want to tell you that n can be a very large number. That's all I want to tell you.
Oh, okay.
So usually you don't define that number n. You won't say that.
Okay, thank
Yeah?
you.
All right. So let's have some fun with this. There's only one correct answer here. Can you do that?
He's doing okay, so you're gonna look.
Are you okay, Lana? What happened?
I always do. Not that when we did like the first hour one,
All right, I'm going to give you a tip. Okay, so for a question like the one that you're looking at right now, it is really easy for you to get confused by the options. Okay, so for those questions, without using the elimination method, I highly encourage you to come up with the answer first yourself and then look at the options. Okay, so that's the best way to approach them. Otherwise, I've seen time and again people getting lost within the trees, not the trees, like the options. Yeah, so don't let that happen. Now you are given something like this. Okay, so carbon, 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 carbon is repeated over and over. You will still do this. I'm going to just get you a hint. Okay, so we have CH3, 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 CH. This is our polymer, right? The others are all hydrogens. Okay, hydrogens, hydrogens, hydrogen, 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 and hydrogen. Again, like I said before, you always pick any two carbon atoms from the chain. Okay, so any two carbon atoms from the chain, any two, totally randomly. I can close my eyes and pick them. Okay, seriously. Okay, so let's pick. I don't know. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, anyway, this. Totally randomly, I just picked that. Oh, maybe let's say that you don't like it. Okay, pick another one. Okay, you can pick anything. Anyway, so let's say that this is my 1, this is my 2. Okay, so I just draw them again. So here's my 1, here's my 2. To 1, I see that I have a CH3 bonded. Okay, I'm gonna draw that. Okay, and then I'm gonna draw the rest of that. This is my 1, my 2. Okay. So here's my hydrogen, here's my hydrogen, and hydrogen. And instead of drawing 2 bonds coming out to bond with the others, I'm going to introduce a double bond between the 2 carbon atoms. That's it, done. This is my monomer. This is my monomer. And if you want to make it a line structure, I do the same thing. So my ensembles are carbon. So here's my 2. This is 1. You know that? 1, 2. The 2, I have a CH3 bonded. So CH3 again is going to be like that. And then between 1 and 2, I have a double bond. So that's going to be the line structure of my monomer. Done. That's it. That's all you had to do. Alana, did you see that? Yeah.
So this is correct. I mean, it's right there. It's upside down. Yeah. Okay.
All right. So with that, going to close that. I'm going to skip this one because I'm going to show you what we're going to be doing. So I'm going to have a preview of coming attractions when it comes to how we apply intermolecular forces to polymers. Okay. So to understand the properties of polymers, again, we'll be using the intermolecular forces. Okay. Stronger the intermolecular forces, stronger the polymer, higher the melting point, higher the viscosity, higher the, all those good stuff. Okay. So anyway, so to do that, we're looking at 2 scales, the chain scale, which is the entire chain or entire polymer, and the monomeric scale. Okay. So first, let's consider the monomeric scale. And here's how you could be presented questions from the monomeric scale. Okay. So let's say that you have, let's see, I didn't hear this sneezing, but anyway. All right. So here are 3 polymers. What I want you to do is I want you to tell me which polymer do you expect to be water soluble? Go ahead.
It's the same thing,
All right. So we have more than 90% responses. Okay. All right. I need your help now really quickly. Okay. So the first polymer. Now pay attention for a minute. First polymer is called Teflon. Okay. We already have a problem with Teflon. Okay. It's in baby blood already. Okay. Can you imagine Teflon being soluble in water? Can you imagine that? No, right? So that cannot be Teflon, cannot be soluble in water. It is not, it's highly inert. Okay. So anyway, the second polymer. How many of you have the second polymer at home? Or how many of you have used second polymer for anything? Don't you guys go to parties? Really? No, don't have time for that. Okay. What are those? Right. Anyway, so I don't know if you are going to when I was an undergrad, I went to parties, a lot of parties. Okay. So they used to have like cups made of that polymer called styrofoam cups. They have styrofoam plates, styrofoam cups. Okay, we even like I don't know, put water or juice in it, and then we even drank from that. It did not dissolve in water. Okay, so the second polymer is called styrofoam. Guess what? It doesn't dissolve in water. What about the third one? Does anybody have the third polymer at home? Really? I don't believe you. So, have you heard about these things called Tide Pods, like detergent packets? Yeah. So those packets are made of that polymer called polyvinyl alcohol. Okay. So that readily dissolves in water. Okay. That's why they're used to make those Tide Pods, and also in hospitals they have plastic bags made of polyvinyl alcohol, that polymer. Okay. They put dirty laundry in there and they throw it in the washing machines. Okay. They dissolve right into water. Okay. Anyway, why does the third polymer dissolve in water? How do you explain that? Please, everybody, I know that you know it. Why does the third polymer dissolve in water? Like interacts with like. See how easy that is now? That's why we talked about this. Okay? The application part, intermolecular force application part is much more straightforward. Yeah? Like, all right. So with that, I think it's time. Okay. All right. 92% of us selected. That's wonderful. All right, here's the attendance code. So have fun tomorrow with the quiz. And when we come back on Thursday, we will have a little bit more fun with polymers, like, application of intermolecular forces to polymers. And then we'll review. So use the review material I posted on D2L to review for the exam as well, okay? All right, bye, everybody.